Have you ever been, completely amazed by a generative AI writing this beautiful, intricate poem, only to watch it completely drop the ball on a basic multi-step logic puzzle 5 minutes later? I mean, it's incredibly frustrating, right? But what if I told you that we can completely fix this logical blind spot today? And no, the secret doesn't require waiting around for some massive new AI model to be released. Instead, as we'll explore in this explainer, we can solve this by using problem-solving strategies directly inspired by how we actually teach children to learn.
Okay, let's just quickly glance at our roadmap for today. We're going to start with the prompting evolution, then get right into least to most prompting. After that, we'll test it out on a customer's service scenario, scale up the complexity with the concatenation puzzle, and then finish up with some pretty dramatic results.
Section 1. The Prompting Evolution, Pushing the Limits of AI.
So we all know standard prompts are fantastic for simple tasks, but eventually they just hit a hard wall when faced with complex, multi-step problems, which leads us to a really fascinating question. How do you get an AI to solve a problem that usually fails? I mean, if asking it to just think harder doesn't work, we clearly need a structural solution to bypass those reasoning limits.
Section 2. Enter least to most prompting, the ultimate logic framework. Well, human ingenuity has developed what we can basically call a new level 3 of prompting. Let's break down exactly what this is. Least to most prompting, or LTM for short, takes a complex problem, breaks it down into simpler subproblems, and then solves them sequentially. But here is the absolute key to the whole thing. It uses the output from the previous subproblem as the new input for the next one. It's directly inspired by real-world educational strategies. Think about it. When a math teacher gives a kid a tough word problem, they teach them to break it into pieces, solve step 1, and then use that specific answer to solve step 2. We're literally just applying that exact same pedagogy to an AI.
To really wrap our heads around this, let's compare it to another popular technique you might know, chain of thought prompting. Think of it using a pass-the-baton analogy. Chain of thought features isolated, independent steps. The AI kind of thinks out loud, sure, but it isn't structurally forced to carry its work forward. Least to most prompting, on the other hand, it's like a relay race. The concrete answer from step 1 is handed directly into the prompt for step 2. It essentially guarantees the AI doesn't drop the context as things get messy.
Section 3. Case Study. Customer Service. A real-world application.
Now, it's one thing to talk theory, but let's actually see this applied to a totally everyday retail headache. Picture this. A customer bought a $30 shirt at 40% off on March 1st. Today is March 29th, there's a new 50% discount on all shirts, and this customer is totally trying to game the system to see if they can return the old shirt and get enough store credit to buy 2 new ones. If you just feed this massive block of text into a standard prompt, the AI gets completely overwhelmed trying to calculate dates, percentages, and store credit all at once, and, well, it completely hallucinates the wrong answer.
But here's where the magic really happens. When that standard prompt failed, researchers appended this exact, super-specific instruction to the end of the prompt. What subproblems must be solved before answering the inquiry? And wow, this forced the AI to stop blindly guessing and instead map out the 4 distinct hurdles it needed to calculate: the 30-day window, the store credit amount, the cost of the 2 new shirts, and finally, whether the credit actually covers that cost.
So they took the AI's list and then just asked it to solve the very first subproblem, determining if the customer is within the 30-day return window. And this is amazing. By forcing it to focus on just that first tiny step, the AI confirmed the window and then actually proceeded to flawlessly solve the entire rest of the complex math puzzle regarding the store credit. Breaking it down structurally literally saved the AI from its own confusion.
Section 4. The concatenation puzzle, scaling the complexity.
Okay, basic math is great and all, but let's escalate the stakes to a notoriously difficult logic test for language models. The task is concatenation, specifically smashing together the last letters of long lists of words. For example, taking think, machine, and learning. The last letters are K, E, and G, which combines into keg. Standard prompting fails this instantly. Chain of thought works briefly for really short lists, but completely breaks down on longer ones. Why? Because the AI tries to hold way too many isolated letters in its working memory at once, and it just loses track.
But notice how least to most prompting explicitly reformulates the steps here. Instead of finding all the letters and combining them at the very end, it constantly restates the previous concatenation. It literally says, the letters for think and machine make key. The last letter of learning is G. Combining key and G gives keg. It only ever has to do a tiny bit of work at each step. This drastically reduces the AI's cognitive overload.
And the results? They speak for themselves.
When tested on a massive 12-word concatenation problem, Chain of Thought managed a pretty meager 34% accuracy. But least to most, it achieved a massive 74% accuracy. This stark contrast proves that carrying the result incrementally along works absolute wonders for AI logic.
Section 5. The dramatic results. Dominating the benchmarks.
All right, this is where we put this technique through the ultimate stress test. It's called the SCAN benchmark. This requires an AI to convert natural human language into rigid, code-like action sequences. For example, translating run left and walk twice into turn left plus run plus walk times 2. Language models notoriously fail at this kind of compositional generalization when sequences are longer than what they trained on. It is a brutal test of true logic.
To conquer this, Least to Most uses two distinct prompts in sequence. Step 1 is reduction. This reduces complex phrases like jump around left twice into much simpler human language steps. Step 2 is mapping. It takes that newly simplified language and directly translates it into the compressed code sequences. So, when researchers ran this brutal benchmark using the exact same TextDaVinci 002 model, standard prompting achieved a totally dismal 6% success rate. Least to Most prompting rocketed that up to an incredibly impressive 76%. Let that sink in. It's the exact same AI brain, just guided by a vastly superior framework.
But wait, it actually gets even better. When researchers paired the Least to Most framework with the more code-optimized CodeDaVinci 002 model, it achieved a near-perfect 99.7% success rate on the SCAN benchmark. 99.7! It essentially solved a problem that language models previously found completely impossible.
Let's quickly wrap up with our key takeaways from this explainer. Least to Most prompting provides significantly improved accuracy over standard chain of thought. It increases the AI's ability to generalize and actually solve problems harder than those it was shown in its prompt, and it results in dramatically better compositional logic. By breaking down complex problems and feeding solutions forward, we are creating a massive leap in how we control and leverage these models for our own workflows.
Which leaves us with this final, provocative thought for you to take away today. What seemingly impossible problem could your AI solve today if you just taught it to pass the baton? Seriously, try the Least to Most framework on your most frustrating AI failures, and you might just be blown away by the results. Thanks for exploring this with us.